Alright, in today's video we're looking at some more advanced problems from the grade 12 regular chemistry class. We're going to take a look at how to solve equilibrium problems that involve ice tables using algebra, as well as ice tables and the reaction quotient, and we'll talk about that in just a little bit. So first off, here's a question where we're given an equilibrium with hydrogen iodide decomposing to make hydrogen and iodine gas. And we're told that at a certain temperature the Kc value is given, 1.84. 10.0 grams of HI gas is put into a 500 ml flask at that same temperature, and it's allowed to reach equilibrium. So it decomposes and reaches equilibrium. What mass of HI, hydrogen iodide, will remain in the flask at equilibrium? If you think you know what you're doing, pause the video and set it up and try to solve it. So I'm going to set up an ice table because we know what was put into the flask, and we're asked what will be present at equilibrium. So the key that we know the initial situation and we're asked about the equilibrium situation is how I know to set up the ice table. So 2 HIs, I like to write out the balanced equation, forms H2 and I2. The initial concentrations, we have to put concentrations into the ice table. We're not exactly told the concentration, but we're told 10 grams of HI was put into the 500 ml flask. So to get the initial HI concentration, we have to do some work. There's two ways to do that. One would be to set up some formulas. We could calculate the moles of HI initially by taking its mass and dividing by its molar mass. Then we could find the concentration by taking the moles and dividing by the volume of the container in liters. Those are two different ways, two different steps in finding the initial concentration. Instead of using formulas, I'm going to use some unit multipliers. So we were told you have 10 grams, 10.0 grams of HI. So with my first unit multiplier, I'm going to do this step of finding the moles. So I'll switch the grams to moles of HI. In my second step, I'm going to take my moles and divide by the volume. Since I'm just dividing, I'll put a 1 on top of this multiplier, and I'll divide by the volume. Now if you want, you could do mental math and convert the 500 milliliters into liters and then put that here, but I'm going to instead set it up by dividing by the volume in milliliters, then converting the milliliters into liters with another unit multiplier. So when you notice the units canceling, the grams will cancel, the milliliters will cancel, and I'll be left with moles per liter, which is concentration. So 1 mole of HI, I grab a periodic table and look up its molar mass, will be 127.91 grams. The volume of the container was 500.0 milliliters. We're going to divide by the volume. And then there's 1,000 milliliters in 1 liter to convert the milliliters to liters. Grabbing a calculator and evaluating that, we get 0.156 molarity of HI initially. Okay, so there's the initial concentration of the HI. So in my ice table, that's going to go on the initial line underneath the HI. There was nothing else placed in the container, so the hydrogen and the iodine start off at 0. Now, we don't know any other numbers to put into the ice table. We don't know any of the equilibrium concentrations, and we don't know any of the changes. So that's the clue that we're needing to insert algebra, insert x's into the table. I can tell right away that because these two start with nothing, they have to increase. So I know this reaction then is going forwards because it's making more of the product, and therefore the HI will have to decrease. But how much do they increase and decrease by? I'm going to look at the coefficients to help with that. So the HI has a 2 in front of it, so the easiest thing is to let it lose 2x. Now when I figure out the hydrogen, I can use the 1 to 2 ratio to say it'll be half of this. Half of 2x is 1x. And then the iodine will be the same thing as the hydrogen because its coefficients are in a 1 to 1 ratio. So at equilibrium, we'll have 0.156 minus 2x for HI. We'll have 0 plus x, we'll have x for hydrogen, and we'll have x for iodine. If we've filled in the table using algebra, then we're going to need to set up an equation to solve for x. The equation we're going to set up, of course, is the equilibrium expression. The Kc for this reaction is equal to the concentration of hydrogen at equilibrium times the iodine concentration at equilibrium divided by the Hi concentration squared. Products over reactants, and the exponents in the expression are the coefficients from the balanced equation. When there's more than one reactant or product, we multiply their concentrations. This was a homogeneous equilibrium. Everything was in the same phase and everything was gaseous, so everything gets included in the Kc expression. So putting these algebraic expressions into the Kc expression, we get that the Kc is equal to x times x, or x squared, divided by 0.156 minus 2x, which I'll put in brackets because it has to be squared. And we were told up in the question earlier that the Kc value is equal to 1.84. So we can let this equal 1.84. Now we have a math equation in front of us. There's two options to solve this. Well, three options, I suppose. If you really feel brave, you could expand the denominator, which will lead from a binomial to a trinomial expression. Then, doing some algebra, you can rearrange and get a quadratic equation and use the quadratic formula to find x. I'm not going to do all that work. Instead, I'm noticing that the numerator and the denominator are both being squared. So one way to simplify this, because they're both being squared, would be to square root the entire equation. You square root both sides. So when I square root on the left side, instead of x squared, we have x. And instead of 0.156 minus 2x squared, we have 0.156 minus 2x. On the right, when we square root 1.84, we get 1.36. Now we've turned a really ugly grade 10 algebra question into a moderately ugly grade 9 math equation. So to solve, we'll multiply the 1.36 by the denominator, so x will equal 1.36 times 0.156 minus 2x. Then we'll expand through. X will equal 0.212 minus 2.72 x's, so that's multiplying like that, the distributive property. And then, collecting like terms, we'll bring this 2.72x to the left-hand side here. We'll get 3.72 x's is equal to 0.212. And finally, dividing both sides by 3.72, we find out that x is 0.057 molarity. Okay, I'm being a little tiny bit lazy with my significant digits there, but I'm okay with that here. The other option, of course, if you own a graphing calculator, would be to use the solver feature, and I'm going to use the TI-84 to illustrate this. If you have a graphing calculator like a TI-83, TI-84, it'll work pretty much the same way as this. If you have the TI-Inspire, it's a little tiny bit different. Now this is a newer TI-84 Plus, so it's got a slightly different solver than the original. So I'll just quickly show both. You press the Math button on the calculator, okay, so this button here that says Math, and you scroll to the bottom or just go up and you'll see an option that says Numeric Solver. Select that, and it asks you now to enter two equations, E1 and E2. What we're going to do is take this equation that we're trying to solve, and we're going to consider the stuff on the left to be E1 and the stuff on the right to be E2. So I'll enter both of those equations on the calculator. E1 then will be x squared divided by bracket 0.156 minus 2x, close the bracket, squared, and then I'll press enter to go to the next equation. I'll clear this because there was already one equation there. And on the right hand side I'm going to put 1.84. So there's my second equation. Press enter. And the way the calculator works, I can see my equation at the top, is it wants me to suggest an answer. give it a guess for x, and then it will find the correct answer closest to the guess that I'm going to give it. In chemistry, because most of our answers to these questions are small positive numbers, 0 is almost always a pretty good guess for what x will be. It'll then tell me an answer that's close to 0. To do this, you press the green alpha button, and then right above the enter button it says solve, so alpha solve. And there we see it 0.05699 or 0.057. So I'll say that x equals 0.057, or I guess more specifically 570 molarity. And that's all you would need to write for me on a test or exam, that you're using the solver and that x equals this. Now if you've got the older TI-83s, 84s, here's an older one, they work in a similar way. You press the math button, you go to the solver feature, press enter. If you've used it before, you'll have to press the up arrow and then clear the equation. Otherwise, this is what you'd see, equation solver, and then equation 0 equals. Now that's a little bit of a peculiar thing. It wants the equation typed in as 0 equals. But our equation said x squared over this stuff equals 1.84. So to make it say 0 equals, we can just subtract 1.84 from both sides. And then we'd have a 0 over here on the right. So I'm going to enter my equation as x, whoops, I just pressed the wrong button. I'll go back to math and then the solver. So 0 equals x squared divided by bracket 0.156 minus 2x, close the bracket, squared. And now to make it say 0 equals, we had to subtract the Kc value, 1.84. And then press enter. And now again, we can see the equation at the top, and then in the middle, we want to know a guess. So again, the guess that's useful for most chemistry problems is that x is 0. So it'll tell me the answer that's closest to 0. So alpha, the green button, and then solve right above the enter button, and we get the same answer, 0.0570 molarity. So there's the value for x. Now we're not done the question. The question was what mass of HI would remain in the container at equilibrium. So what I'm going to do first is find the concentration. So I'll say therefore the concentration of HI at equilibrium, I'll just put an EQ beside that, is equal to 0.156 minus 2x. That comes from my ice table, the equilibrium expression for HI. And then plugging that value for x in, we're going to get 0.156 minus 2 times 0.057. So we're going to get 0.0420, I guess 0.042 to 3 decimal places, molarity. There's the concentration of HI at equilibrium. Now to convert that back to grams of HI, we could again go back and use these formulas. We know the concentration and the volume of the container, so you could find the moles. Then when we know the moles and the molar mass of HI, we could find the mass. I'll again use unit multipliers though. And the key for me is that you should never start unit multipliers with a unit multiplier. This 0.042 molarity is really 0.042 moles of HI per liter. So really it is a unit multiplier. So I'm not going to start my unit multipliers with that. The number that I'm going to start with that's not a unit multiplier was the volume. 500 milliliters was the volume. I'll convert that milliliters into liters. Then, using this concentration, which is 0.042 moles of HI per liter, I can convert the liters to moles of HI. And then finally, using the molar mass, we can switch from moles to grams of HI. So 1 liter has 1,000 milliliters. The concentration of HI at equilibrium was 0.042 moles per liter. And the molar mass of HI hasn't changed. We had it earlier. It was 1 mole is 127.91 grams. Grabbing a calculator, We have 500 divided by 1,000 times 0.042 and times 127.91. I get an answer of 2.69 grams of HI remains at equilibrium. Right? If we wanted to know the hydrogen or the iodine, those were both equal to X. So this 0.0570, the answer we got for X, is the concentration of hydrogen and iodine at equilibrium. We could do a similar kind of calculation to calculate the masses if we wanted to. All right, so you can see the math in this unit of equilibrium is more complicated than the math that we saw in our first unit and on our second unit of kinetics. So this is where you really have to pay some close attention and practice your algebra. Question number 6, and by the way, both of these questions in this video come from a worksheet that I gave out in class. That's why the numbering is a bit odd, number 2 and now number 6. So the reaction here was studied, and it says carbon, and right away the solid symbol jumps out at me. So carbon solid is reacting with CO2 gas to make CO gas. So this is a heterogeneous equilibrium. There's more than one phase present, solids and gases. And the reason that's important is because I remember that solids as well as liquids are not included in equilibrium expressions because their concentrations don't change. The concentration of the solid substance is the same when there's a lot of it at the beginning or when there's just a little bit left at the end. Its concentration has not changed, although the amount definitely does change. So the mass of solid can go up or down, but its concentration doesn't change. So we've got a Kc value given for the reaction. We want to know what would be the carbon monoxide concentration at equilibrium in a 10-liter flask done at this temperature, same temperature as the Kc, when 0.2 moles of carbon dioxide and 1 mole of carbon monoxide are placed in the flask along with 0.5 moles of solid carbon. So let's write out the balanced equation, carbon solid. Now because it's heterogeneous, I'm going to put the phases in because they'll be important. Plus carbon dioxide gas produces 2 carbon monoxide gases. And we're going to set up an ice table. Now because there's solids and gases present, and only gases are going to be included in the Kc expression, I'm going to start by just putting a big X underneath the solid substance, the carbon. All that's important is that if needed, the carbon is in the container to react. We can do some mental math. Concentration is moles divided by liters, the C equals N over V. The volume was 10 liters. So when you have 0.2 moles of carbon dioxide in the flask, 0.2 divided by 10, you have 0.020 molarity carbon dioxide. And 1 mole of carbon monoxide, you have 1 divided by 10, 0.10 molarity carbon monoxide. Now the problem here is that there's initially both gases are present, the reactants and the products. In the last question, if you recall, there were no hydrogen or iodine in the container. And the reason that was important was that if there was none there, we knew the reaction would have to go forwards, so these two things would increase and this would decrease. The problem here is that there are no zeros initially. These things are both present. So I don't know right now what direction this reaction will head. And that's the clue to calculate the reaction quotient. The reaction quotient. It's calculated to determine, number 1, is the reaction at equilibrium, and if it's not, it'll determine, number 2, what direction the reaction will go to reach equilibrium. Its symbol is the capital letter Q, and it's calculated the same way that an equilibrium constant is calculated. So in this case, concentration of CO squared divided by the concentration of CO2. We're leaving out the carbon again because it was solid. Putting the initial concentrations in here, we get 0.10 squared divided by 0.020. And I'm going to calculate that here. So 0.1 squared divided by 0.02, we get a Q is equal to 0.50. Now how does that tell me if we're at equilibrium or not? Well, Kc was 0.15, so I can tell right away that this is not at equilibrium because Q is different from Kc. So since Q is not equal to Kc, the reaction is not at equilibrium. But if that's all I could tell from Q, it wouldn't really be that powerful. I can tell one other thing. I can tell now which direction will it go. Without any zeros, I didn't know whether this would increase or decrease. Would this increase or decrease? We can't tell. But when you look at Q, you notice that Q is actually larger than Kc. Kc in the question was 0.15, and our Q is 0.5. Now why is that important? If Q is bigger than Kc, then not only do I know the reaction is not at equilibrium, but I can tell that Q is going to have to get smaller. Q will have to decrease in order to become equal to Kc. When you look at Q, it's just a fraction. How can it get smaller? Well, to get smaller, a fraction would need a smaller numerator and a larger denominator. So that means I'm going to use up carbon monoxide and produce carbon dioxide. So when Q is bigger than Kc, the reaction will shift backwards. And we can just memorize that if you don't want to reason it out like we've just said here. So when Q is bigger than Kc, you get a backward shift in equilibrium. So that means this reaction will end up losing some carbon monoxide and gaining some carbon dioxide. Using the balanced equation ratios, there's a 2 here, so I'll say it loses 2x. There's a 1 here, so I'll say it gains x. At equilibrium, then, we have 0.020 plus x, and we have 0.10 minus 2x. Now we can plug those things into the Kc expression. Kc was equal to concentration of CO squared over CO2 concentration. And that's equal to 0.10 minus 2x squared over 0.020 plus x. And that's equal to the Kc of 0.15. Now this question, just looking at it mathematically, is a bit of a doofus question because the numerator is being squared, but the denominator is not. So that little trick that we used in the last question of square rooting is not going to work here. The only option, if you don't have a graphing calculator here, would be to expand the numerator and then rearrange to get a quadratic equation and then use the quadratic formula to solve for x. You'll get 2 answers almost certainly from the quadratic formula, but only one of those 2 answers will make sense in the chemistry, because x, of course, cannot be a negative number. It has to be positive, so if you get a negative answer from your quadratic equation, you would ignore it. But also, notice here where it says 0.1 take away 2x is the concentration at equilibrium. Well, that means that x cannot be bigger than 0.05. Because if it were bigger than 0.05, then 0.1 take away 2 times x would be negative as well. So you can't have a negative concentration. X would have to be bigger than 0 and less than 0.05. So we would ignore any x's from the quadratic equation that did not fit that description. I'm not going to take time here to go through the quadratic equation, and on a test or exam with me, you would never have to do that on a chemistry test or exam in grade 12 chemistry. So what I'm going to do is just use the solver. So using my solver, and I'll use the newer calculator again. So press the math button, go up to the numeric solver, clear the previous equation. So my one equation is this, so bracket 0.1 take away 2x, close bracket, squared, divided by, open another bracket, 0.02 plus x, and then press enter. And my second equation is the 0.15. And I'm saying this equation equals this equation, which is what we see here. Press enter. And again, a guess that almost always works in chemistry is that x is 0. So I'm going to use x equals 0 as a guess. I'll press the alpha button, and then above the enter it says solve. Done. So x is equal to 0.014 molarity. For those of you with the older TI-83s, 84s, again, we'll quickly do that here. So press the math button, go to the solver feature, press enter, go up arrow, clear whatever equation might be there, and then type your equation in, but again, it has to say 0 equals. So we're going to take this expression on the left and minus 0.15 to have 0 equals on the right. So bracket 0.1 minus 2x, close the bracket, squared divided by bracket 0.02 plus x, close the bracket, and then again minus 0.15, the Kc. Okay, press enter, and again give it a guess that x is approximately 0, and alpha solve, we get the same result, that x is 0.014 molarity. Now, did we answer the question? The question is, what will be the carbon monoxide concentration at equilibrium? So we can now say, therefore, the carbon monoxide concentration at equilibrium, looking up at our ice table, it's going to be 0.1 take away 2x. So let's write that. 0.10 minus 2x will be 0.10 minus 2 times 0.014 is equal to 0.1 take away 2 times 0.014 is 0.072 molarity. There's the concentration of the carbon monoxide. If we wanted to know the concentration of carbon dioxide, we would take 0.020 and add our x value to that. All right, so there's again a question where the initial line of the ice table had no zeros on it, so we did not know the direction that this reaction would go. That's the clue to set up the reaction quotient. Now, there was also a solid in this reaction, so we put a big X under it. It's not part of the equilibrium expression, so we didn't need to worry about it. The fact that the question told me the moles of the solid is irrelevant. We didn't have to use that information. Now, when we calculated Q, we used the initial conditions, and we found out that Q was not equal to Kc. So the reaction then was not at equilibrium. Because Q was bigger than Kc, Q would have to get smaller, and the only way for the fraction to get smaller would be to decrease its numerator, have a smaller numerator, and a bigger denominator. So that means you needed less CO and more CO2. Less CO meant that the CO's concentration would drop, and more CO2 meant that the CO2's concentration would go up. We used algebra to fill in the table because there were no other numbers, so minus 2x and plus x. Now, taking the equilibrium expression and plugging that algebra in, setting it into equal to Kc, we looked and saw that the algebra here was really nasty without a calculator, because a squared and then a no squared in the denominator would make it impossible to just square root to simplify the equation. So we'd have to solve that using the quadratic equation. Rather than do that, we solved it with the solver, found x, and then plugged that into the expression for CO at equilibrium to get the answer to the question. Okay, so the reaction quotient tells you whether you're at equilibrium, and if not, it can tell you what direction to go to reach equilibrium, which will tell you where to put the minuses and pluses in your change line of the ice table. So I hope that helps with some more advanced equilibrium problems in grade 12 chemistry.